Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on electromagnetic induction from March 2021, paper 4, variant 2. In this question, we will talk about magnetic flux linkage, eddy currents, and some other important points about electromagnetic induction. And we will discuss these points by solving past paper question. For question number 9, part A, we need to define magnetic flux linkage. First of all, let's try to understand magnetic flux linkage with the help of formula. Magnetic flux linkage is simply equal to number of turns of coil times magnetic flux. But magnetic flux is equal to B times A is equal to B times A. B is magnetic flux density. So we can write on here B is magnetic flux density. B is magnetic flux density and A is cross-sectional area. So we can say A is cross-sectional area of coil. So we can write down magnetic flux linkage is equal to N times BA. So this is how we can write down equation for magnetic flux linkage. Now let me show you how you can write down the answer for this question. This is how you can write down the answer. For the first part, we have said the product of magnetic flux means magnetic flux and the number of turns of coil. So we have defined this one. Magnetic flux linkage is equal to N times magnetic flux. In the second part, we have defined what is magnetic flux. So we have said magnetic flux is the product of the magnetic flux density normal to the plane of the coil. Very important point. You have to mention normal to the plane of the coil. Means these magnetic lines normal to the plane of the coil. So we have to consider this component of magnetic flux density. This one is the plane of the coil and normal to the plane of the coil. Very important part. So this is the plane of the coil. So the magnetic flux density normal to the plane of the coil. This part is very important and this one has one mark. And the next one, cross-sectional area of the coil. So this is how you can define magnetic flux linkage. And if you look at number of turns of this coil, so this is one turn. This one is the second one, third one, fourth, fifth, sixth, 7, 8, 9, 10. So this coil has 10 number of turns. For part B, it is given to us a solenoid of diameter 6.0 centimeters and 540 turns is placed in a uniform magnetic field, as shown in figure 9.1. This coil has 540 turns and the diameter of this one is 6.0 centimeters. If you look at cross-sectional area of this solenoid, we can draw area normal vector. So this is area normal vector and this is B, magnetic flux density. And the angle between these two is equal to 0 degrees. So theta simply we can say between A and B, this is equal to 0 degrees. For this question, it is also given to us the variation with time t of the magnetic flux density is shown in figure 9.2. On y-axis, we have magnetic flux density and this is in milliteslas. And on x-axis, we have time and time is in seconds. For this question, we need to calculate the maximum magnitude of the induced EMF in the solenoid. So let's try to understand how we can calculate induced EMF. Induced EMF is equal to negative d phi by dt. And this is only true if the coil has only one turn. That in this case, coil has n number of turns. So it means this is equal to rate of change of magnetic flux linkage. And magnetic flux linkage is equal to NBA cosine of theta. And theta is the angle between A and B. For this question, it is given to us angle between A and B is equal to 0 degrees. So cosine of 0 degrees is equal to 1. So simply we can write down is equal to 1. Then we can write down EMF induced. This is equal to d by dt times NBA. But for this question, n is constant, mean coil has fixed number of turns and cross-sectional area of the coil is also fixed. So these two are constant, so we can take them out. So we have negative NA and this is d by dt. We need to calculate d by dt. It simply means that we need to calculate the gradient of this graph. Question is asking us when maximum value of EMF, and value of EMF is maximum when d by dt is maximum, means when this quantity is maximum, and this quantity is maximum when the gradient is maximum. So the gradient is maximum here. In this part, gradient is maximum. So it means here EMF induced is maximum. So here EMF induced is maximum. So we have to calculate the gradient of this line. We can write down here maximum EMF induced. This is equal to negative number of turns we have 540 and cross-sectional area we can write down is pi r square and we have to multiply with the gradient. So d by dt is simply equal to gradient. So we can write down this is the gradient. We need to plug in values. So we have negative 540. We have pi radius is equal to 3.0 centimeters. So we can write down 3.0 centimeters. So multiply with 10 to negative 2 square of this gradient. So at this point we have this is 250 and here we have 0. So it means 0 minus 250, but this is in millitesla. So we have to multiply 10 to negative 3 divided by time. This is from 6 to 7.2. So it means the time in this case is 7.2. We can write down minus 6. We can solve this one and we can find out final answer. So the final answer in this case will be equal to 0.318 or simply we can say is equal to 0.32 volts. So this is our final answer. For part C, it is given to us we have a plate of copper and this is supported by a rod, and this copper plate is placed between poles of magnet. Then we displace this one to one side and then release it so that it oscillates. A motion sensor is used to record the displacement of X. For this question, it is also given to us a second thin copper sheet Y replaces X. Y has the same overall dimensions as X but is cut into the shape shown in figure 9.4. The motion sensor is again used to record the displacement. In figure 9.5 shows the variation with time t of the displacement S of each copper sheet. For part C1, we need to state the name of the phenomenon, illustrated by the reduction in the amplitude of the dashed line. If you look at dashed line, so it has this much amplitude here and then it has this amplitude here, and at the beginning amplitude is this. So if we draw and connect these points, we will get exponential decay like this. We can also connect these points to get better picture of this. So if we connect these points, so this is also exponential decay. As this is exponential decay, so simply we can say in this case amplitude decreases gradually and exponentially. So this is light damping. So simply we can say this is light damping. That's all what we need to do for this question. Simply we need to write down this is light damping. For the second part, we need to deduce which copper sheet is represented by the dashed line, and we need to explain our answer using principles of electromagnetic induction. So this one is X and this one is Y. We need to find out which copper sheet is represented by this dashed line. That is what we need to find out, and we need to explain our answer using principle of electromagnetic induction. First of all, let me show you what is happening in this case with the help of animation, and then we will come back and we will write down the answer for this question. Let's try to understand the motion of the solid plate and slotted plate inside magnetic field. Simply you need to look at motion of these two plates and you need to understand the difference between motion of these two plates, and then I will explain to you why the motion of these these two plates inside same magnetic field is different. And this is what C2 is asking us. And then we will explain why the motion of these two plates is different using principles of electromagnetic induction. In this case, you can see we have a solid plate. If I move this solid plate outside of the magnetic field and then let it go, you will see after very short time, this plate will stop. So we will simply say, in this case, the time taken by the solid plate is very short time. So we can say this time is very short time. Now, if we replace this plate with slotted plate, so this one is slotted one, and leave it from the same height, you will see this will take very long time. So this slotted plates take long time. So we can write down it will take long time. So you can see from here, motion of solid and slotted plate inside the uniform magnetic field is different. Or we can simply say very short time simply means that energy dissipated very quickly in first case. Energy dissipated quickly. So we can say energy dissipated quickly. Or simply you can say, in this case, mechanical energy converted into electrical, and electrical finally converted into thermal energy. And time taken in this process is very short time. But for slotted plate, time taken is longer. Now we will explain this one using principle of electromagnetic induction. In the animation, we have seen that time taken by the solid plate was very short time. Solid plate, time taken was very short time. But the time taken by the slotted plate was very long. So we can say slotted plate, long time. Now we have to use this fact and we need to find out which curve is represented by the solid plate and which one is represented by the slotted plate. Now if you look at first of all at solid curve, mean this curve, the amplitude of this one is not decreasing with time. So it simply means this will take longer time to stop. Longer time to stop, it simply means that this one is slotted plate. So we can say this one is slotted plate. We can write on here. This one is slotted plate. If you look at dashed line, time taken is short because its amplitude is decreasing with time. So it will take shorter time to stop. And shorter time is taken by solid plate. Solid plate. And solid plate, X is the solid plate. So we can say X is solid plate. So shorter time is taken by solid plate and longer time is taken by Y. And this one is slotted plate. Question is asking dashed line. So dashed line is representing solid plate, or we can say is representing copper sheet X. So this is 1 mark. If you write down this one, you will get 1 mark. Now we need to explain this one using principle of electromagnetic induction. So first thing we need to understand, when this plate is oscillating inside the magnetic field, so the oscillating plate will cut magnetic flux. So we can simply write down oscillating plate. This will cut magnetic flux lines. You can say cut magnetic flux lines. Or simply you can say cut magnetic flux. As magnetic flux is cut and rate of change of cutting magnetic flux, this causes induced EMF. So we can simply say in this case, induced EMF is produced, mean EMF is induced in the plate. And due to induced EMF, there will be eddy currents induced, mean induced current means when the conductor is inside changing magnetic field, our conductor is cutting magnetic flux lines, current is induced, and that current we call is eddy current. So it simply means that in this case, mechanical energy of the plate will be converted into electrical energy. So this is electrical energy. Electrical energy. So it will be converted into electrical energy. And these eddy currents, they are different. They are different in solid plate and they are different in slotted plate. If surface area is large, eddy currents are large. Surface area. If the surface area is larger, it means eddy currents are larger. So eddy currents, we can say in plate X, I can say I is representing eddy currents. In X will be greater than Y because the surface area of X is greater than surface area of Y. It simply means that energy will be dissipated very quickly in solid plate. Means its mechanical energy will be converted into electrical, and then electrical will be converted into thermal due to eddy currents. Because conductor has also resistance, so the electrical energy will be converted into thermal energy. And that's all what we need to write down for this question. Let me show you the answer, how you can write down the answer. This is how you can write down your answer. First thing, you can say copper sheet X, as we have already written. You will get 1 mark. So you will get 1 mark for this one. Copper sheet cuts magnetic flux when it oscillates between the magnetic poles, and EMF is induced. So we have discussed EMF induced. EMF induced, it will cause eddy currents. And eddy currents in X is greater because it has greater surface area. So greater energy is lost in X as compared with Y. So the dash curve represents copper sheet. This is how you need to write down answer in a very systematic way. If you write down these points, you will get 4 marks. And total marks for this question are 4.